start recording, and we're gonna move to actual class thingy. Okay. So I'm planning to bring more clicker question this semester than last semester. So you see the hair is rising. So why does this happen? So what do you think? Thirty more seconds. Once you choose answer, also try to explain to yourself why that is the correct answer. Okay. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. So mostly A, it is because of electrostatics. Yeah, that's what that is. But is there better choice? Okay, we need to look at that one as well. Similarly charged, hair attracting each other. So similar charges, they don't attract, they repel. Okay, so C says similarly charged hair repelling each other. So that's another possibility. Let's see which one is better and more specific, right? So A and C possibilities, just like many of you chose. Oppositely charged hair repelling each other. So oppositely charged, opposite charges, they don't repel, they attract again, okay? And in this case, they are not attracting, they are repelling. That's why they want to go away from each other. If they are attracting, all the hair would be sticking together, okay? So seems like A and C are correct answer, but C is more specific. It tells you why. So that's why C is the best answer for this question, okay? So what happens when we take up our clothes during the winter, for example, the jacket, and you drop that jacket, inner side of the jacket in your hair may rise. Even without rubbing it, sometimes your hair may rise. So what happens is when we rub one object with another object, the charge transfer takes place. So that's how our hair, our body gets charged. And since they are similar kind of charges, what happens? They repel. So that's why these hairs are sticking. So they are trying to get out from your head, but of course, your head is holding them. So that's why they are not flying off. They are just rising. Okay. So we can charge object by rubbing, and that's called charging by friction. So in that case, one kind of object becomes positively charged, another kind of object becomes negatively charged. And which one becomes what kind of charge depends on their property. So to actually, understand that, we have to go to the, let's say, all the way inside how the electrons are inside the atom and how many electrons are in the outermost cell. So we're not going to do that details here. We'll just, understand that there are going to be two kind of charges. And why there are two kind of charges? Because every atom, every matter has atoms, and atoms have electrons. And we say, okay, whatever charge they have, we call that, we say that charge is negative. And there are protons that's inside the nucleus, and their charge is opposite of the electrons, and we call them positive charge. Okay. So now with that, any question you have about that question? Okay. Feel free to ask me question without me asking you question, like saying, do you have question? Okay. Interrupt me anytime you like, or write that on the chat. When you write that on the chat, pull down and say everyone and write it down. Okay. That way everyone can see the question, so that when I am answering, they would know what answer I am giving. Okay. So now, okay, so here is this question. And since there are only two choices, let's spend just 30 seconds on it. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see how did we do here. So mostly B. So neutral means no net charge. Yes. Everything has charge, because everything, they are made up of electrons and protons. They have charges, means everything have charge. But when there is equal number of positive and negative charge, net charge becomes 0. Okay, they neutralize each other. So for example, we can think of a matter something like this. It has an equal number of positive and negative charges. So that means everything has charge. But when we say it's uncharged, it's a neutral, that means there is no extra charge. So for example, if I were to pull one electron out from here, then there are going to be one less electron than the proton, positive charge, right? One less negative charge means now it is positively charged when you remove one electron, okay? And both electron and proton, they have same amount of charge, but their property is opposite, okay? So how do we find what is net charge? So for example, just like I said, if I were to take that one electron out from here, then there's going to be one extra proton. And once we use our knowledge how much charge a proton has, we can tell how much extra charge now this object has. Okay, so we can do that. So that's what I'm talking about here. So here is first equation you are seeing, right? So this is Q here means charge. So we denote net charge, total charge, or charge by Q. And this Q could be sometimes uppercase Q, sometimes could be lowercase q. And you see this N with P subscript. So that means number of proton. And this lowercase e is amount of charge, either for electron and proton. It's called fundamental unit of charge. So now what you see here is there is this difference between proton and neutron. Whenever there is difference in number, then they're going to be non-zero. But whenever they are equal, and that's the case for most of the time, then what happens? Neutron and proton, equal number, so 10 proton, 10 neutron, sorry, electron, 10 proton, 10 electron, means 10 minus 10 is 0. So no net charge. So net charge is 0 in that case. But like in previous example, I said, okay, if this one had a 4 proton but 3 electron, then you have this positive, 1 E. So now that much charge we have, and E is charge of an electron, value of one electron or proton, okay? So that's what that is. So now, so what is the value of 1E? Let's see if I remember, 1.6 into sig fig. It is 1.6 times 10 to the power negative 19, and coulomb is the unit of a charge, okay? So that's the value of this. So whenever you see this thingy in the context of charge, that's what this is, okay? You know it, or you can find it. Just type charge of an electron or charge of an proton, okay? It is just a value, okay? And if electron is more, then the net charge is going to be negative. When proton is more, net charge is going to be positive. So that's why the way they are subtracted here, okay? So here is one such example, right? So it says, okay, there is a negatively charged, positively charged metallic sphere. Oh, what is that N? Right? We had a coulomb. What happened that NC now? Non-coulomb? No, that's a nanocoulomb, just like meter has millimeter, micrometer. Similarly, we have coulomb also has millicoulomb, microcoulomb, and even nanocoulomb, picocoulomb. So 1 nanocoulomb means 10 to the power, let's see, 9 coulomb. Okay, it's a very small amount of charge, or I should say, actually, coulomb is large amount of charge. 1 coulomb is large amount of charge. So that's why we have often you see it's going to be in microcoulomb or nanocoulomb. Micro means 10 to the power negative 6 coulomb. So a millionth of a coulomb is 1 microcoulomb. So a negatively charged rod has this much charge. So we have two things, right? A sphere and a rod. So they have charges. So a sphere has a positive 4, and both of them are in nanocoulomb. So I'm not writing that right now. I'm just writing something like this. When the rod touches the sphere, so now you bring it here, what happens? These electrons like to travel around, okay? Especially in the material like metals, we call that conductors, okay? So it says, okay, that many electrons are transferred. So now, out of that, what happened? That many electrons are gone. Now it says, what are the charges of the sphere and the rod? So we add electron, that means we are adding negative charge here, adding negative number. And electron goes out means we are subtracting negative number. So that means negative number is going out here. That means it's going to have less negative. And whatever negative goes here, it combines with the positive. So it's going to have less positive. So that's how it works. Okay. So you are losing negative from negative means it's going to be less, right? But you are adding negative to the positive. So for example, -1 and +2 gives you +1. So positive value decreases, right? So that's what's happening here. What are the charges, right? So now, how much charge is gone from the rod? That's what we want. So here, number of electrons are given. So it's like saying, okay, 5% is out of the room. How much mass is gone, right? So if you know mass of each person, then you add all that masses, so that much masses from the class is gone, and remaining mass is inside the class. So same idea here, that many electrons are there. So electrons have mass, but we're not talking about mass here. We are just talking about charges. And we already learned how much charge an electron has, right? So now if that many number, how many? That many number of electron gone, that means that many number times charge of one electron, that's going to be the total charge gone from the rod, okay? And that's what I'm doing. I'm multiplying this number of electron by amount of charge in an electron. Electron has a negative charge, so that's why I'm putting negative sign in front of this number when I'm using this as a electron. So multiplying that number gives us that many nanocoulomb. So this is gonna be in coulomb. See, this is coulomb, this is number. So this is gonna be in coulomb. So whatever number you get, you can convert that into nanocoulomb by using this conversion factor. Okay, so after you do that, you get this number here. So since these numbers are given in nanocoulomb, I'm writing that in nanocoulomb, but you can convert this in coulomb, you can convert this in coulomb. That way you can just keep this in coulomb as well. Okay, either way. But you need to be able to, just like knowing how to convert a meter into centimeter or millimeter is important. Similarly, knowing how to convert coulomb into nanocoulomb, microcoulomb, and other way around is important as well. Okay, so you need to learn that. It's just dividing numbers, right? So calculator comes in handy for that. So now the amount of charge that left on the rod is initial charge and then whatever is gone. But gone charge is negative. So this negative and negative from here becomes positive. So that's why we have less negative charge now. Okay. So that's the amount of charge we have on the rod. Now, how much charge we have in this sphere, right? So whatever we had initial charge, and you add the charge from the rod. So initially we had positive charge, and from the rod came negative charge. So although we say we are adding, we are subtracting it now. So that's why we have less charge in this case as well. It is nothing more than just arithmetic, okay? Knowing that if you lose negative from negative, they're going to be less negative. But when you add negative on positive, what happens? Less positive. So you need to keep that in mind. And mathematically, you can see that if you keep track of sign. Okay. Okay, so anything you like to add on this or ask? And it could be written in terms of coulomb as well. Okay. So it depends on how the answer is given you. For example, in, let's say, multiple choice question, is the answer in terms of coulomb or in terms of nanocoulomb, right? So that's going to help you whether you need to convert it or not, right? Okay, so I don't hear and see any question. So let's move on. So there is this question here. Why do metals like copper, aluminum, silver, and gold act as a good conductor? So what do you think? 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C, that is correct answer. So in the insulator, other way around, the electrons are, tightly bonded with the other, let's say positive charge, so they are not free. Okay. So now, after knowing what is, conductor and what is insulator is, let's watch this video. So this video is from YouTube. If you have slide, you can copy this, paste on the YouTube and watch if you like, or else I have downloaded it here and I'll play it. Hopefully you can see it. Oh, no sound. Looks like my volume button. Oh, that's 100%. Let me see what happened here. I see it's using wrong speaker.
Benjamin Franklin, back in the mid 1700s, determined through lots of experimentation that there were only two types of charge, and he named one positive and one negative. And this is the basic idea of what he did. He gathered materials. On the left, we see a pair of materials, a rubber rod and a piece of animal fur. On the right, a glass rod and a piece of silk. Those were his original materials. And what he did was basically take the rubber rod and rub it on the piece of fur, and that combination had.
And you can do that by combing your hair with a plastic comb.
Some little object like this, which is a pith ball. It's the really small, really light object that you can see electrical interactions quite easily. Bring it near that, and you see that initially it attracts, and then it repels, and you see this thing now being repelled by this rod. Then took a positively charged rod, and if you take this glass rod, rub it on the silk, and then bring it near, it is definitely attracted. And he did that with a lot of different materials. He took the rubber rod, it was repelled, took the glass rod, it's attracted, took all different materials, only saw repulsion and attraction, and determined that there must be only two types of charge. Named one type of charge negative, and this plastic rod, which is what we use as a replacement for the rubber rod, when rubbed with fur, has a negative charge. His definition: rubber rod, now plastic, when rubbed with fur, picks up a negative charge, or has a negative charge. This glass rod, when rubbed with silk, has a positive charge. Those were his original definitions. Benjamin Franklin.
Okay, so here is a question for you. So you'll have 2 minutes. Think about it, okay, nicely, what you just heard, and from your knowledge. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C, the charge rod induces in a separation of charge in the neutral ball, creating a temporary opposite charge on the side nearest to the rod, causing attraction. Upon contact, the ball becomes similarly charged to the rod, causing repulsion. Perfect. Okay. So initially, the ball doesn't have negative charge. It has a neutral. Okay. The ball initially is a neutral. So this is what happens. And I see a comment on the chat. I can only see Dr. Nungana, not the video. So video was played inside the PowerPoint. So if you're looking at my slides, that's where the video was played. Okay. So I'm going back, look at my slide, the video. Yes, of course, it is old video. It is not HDMI. I mean, not HD quality video. So that's why it's not that, great, but
Benjamin Franklin, back in the mid
hopefully you are the sound.
determined through lots of experimentation that there were only.
But I have also put this link on my slide, and the PDF of the slide is posted inside the folder called class slides on the file tab. Okay, you can go and watch that video if you like. So here we said, okay, it induces charge. That's what it said in the part C. So what does it mean when it say what's going on? So here one charged object was brought near the neutral object. Let's see. So what happens here? Oh, this one I forgot to hide. So there is a neutral object. Now you bring a charge rod. So this is like that pith ball right now. It has equal amount of positive and negative charge. And you bring the positively charged rod, for example, close to it. Then what happens? The negative charge gets attracted towards the positive charge, leaving positive charge behind. So one thing I want to make clear that it's not the positive charges that are moving. It's the negative charge that's moving, okay? So once we have less negative charge in this area, it has now net positive charge. So that's how we need to think. So positive charge don't move in a solid object unless it is floating on the liquid or something like that. Then it can float, move. Otherwise, in solid objects, positive charge cannot move because it is inside the nucleus in that atom, okay? So it's not free to do that. So ions can float in the fluid, but the positive charge itself cannot move in a solid. So how do I think about it? So for example, let's say if it goes on this side, we can say, okay, this one neutralized this positive. So it seems like this positive charge moved here, or I should say over here, but that did not happen. What happened? Since there are still a lot of positive and negative charges than what I'm showing here, what happens when this negative charge goes and neutralized? This extra negative, this one vanishes from there, okay? And since so what happens here? This is gone. One less electron means now there is one more, let's say, proton. We can think of something like that. So that's why one side appears to have more positive charge. That does not mean there is no negative charge on that side. There is still negative charge, but those are less than positive. So whatever I'm drawing here is the extra. So equal number, they are canceling. Whenever we have extra number, that's the number that we are showing here in this drawing, okay? So it is the net charge we're talking about. On this side, there is a net positive charge. On this side, there is net negative charge. But if you look at this whole thing, what happens? Net charge is still zero because same number of negative and positive charges means they neutralize, okay? So this object is still neutral, but polarized. So polarized does not mean object is charged. Now, if it touches, then what happens? When it touches, some of these electrons are going to come here with this positive charge and combine, okay? They are attracted to the positive charge. Whenever they get chance, they come in contact and neutralize the positive charge. So when they contact, what happens is all this electron vanishes from the sphere, leaving you just the positive charge. And if you remove this, then now this is left with just positive charge. So this is another method of charging we call conduction, okay? So for example, water molecule, water we drink, in molecular form, it has 2 hydrogen and 1 oxygen. So what happens is in one side, it has a more positive charge than the negative charge. So it's polarized. So we call this kind of liquid polar liquid, and they are very good solvent because they can stick with the another, charge of the another object. So they cling with the other one, okay, and dissolve those things. So anyway, so we call this is polarized. And when we have this equal amount of positive and negative charge separated by certain distance, then we call that dipole. And this distance here, d, is also known as kind of dipole. Yeah, that along with the other thing, we'll talk a little bit more about dipole moment later. Okay. So this is how the water molecule looks like. So oxygen, it has a more negative on the side, it is on more negative side when it makes the bonding because hydrogen shares 1 electron with the oxygen and leaving hydrogen more positive, okay? So overall, you can think of, okay, the oxygen side has a more negative charge, and hydrogen side, they have more positive charge. So we can think of that as dipole, okay? And this negative charge and this positive charge in hydrogen, they can make bonding. That kind of bonding is called hydrogen bonding. It's not very strong, but there is a bonding, okay? So our heart is made up of, like muscles, and there are fluids, and fluid have salt, and salt can ionize and make, positive and negative charge. So what happens is when our heart is beating, the amount of charge is constantly changing, and the one side of the muscle gets positive charge and another side gets negative, and after instant of time, there's flips and so on. So because of that, what happens is this dipole thing keeps changing direction. And when we are doing ECG, EKG, we are just detecting that signal, okay? So we measure potential. So we'll talk about potential more in another chapter. But that's how keeping track of them can tell us about the health of our heart, okay, body. So that's how these things are used. So science, okay, seems like nothing, but when you learn how it can be used in technology and benefit of human, that's the awesome, right? That's where the awesomeness comes in. Okay. So I just, so one method of charging is just by robbing. And when you rob, what happens? One object becomes positively charged, another one becomes negatively charged because electron transfer from one object to another. So here you see the silk becomes negatively charged, means the electron from the glass rod moves to the silk. Okay. Now, another method is called conduction. I already talked about that one as well. You bring the charged object close. What happens? There is this extra polarization, let's say, and when it touches, this negative charge goes and neutralize that, okay? And then leaving this thing positively charged. Once this rod is gone, they spread, uniformly all over the place. So this is called positively, charged. Oh, by the way, I totally forgot. We usually take a break around 1 hour. So a little late, but let's take break if you have to run to your bathroom or so on. So for the coming classes, every class we take break. So if you can hold, you can hold until we take break and go to the restroom or something like that. Okay. But break is short, just 5 minutes, folks. Okay, folks, so welcome back. So I have a yes/no question for you. Can you see that on the screen? Can insulator be charged by this method? What do you think? Yes or no? Type that on chat, Zoom chat. Okay. Okay, I see a lot of no's. Can somebody explain why no? Turn on your microphone and talk or write it down.
I would say it's because insulators don't have easy electron flow throughout their material.
Right. So electrons are not free to move. So that means if we were to bring something like this not gonna happen there, right? So this insulator gonna get slightly, polarized, but we cannot charge something like this. We have to rob insulator to make it charge. There is no other way around, okay? Yeah, good point. So now another method of charging, what we call induction. So friction requires touching because we are robbing, right? And conduction also requires touching. See, this rod had to touch it, right? It says in contact with conductor, right? But induction, you don't have to touch this object with this rod, for example, okay? So first step on charging by using induction method is to bring closer, and you see here this is polarization, right? So the first step is polarization, and in my note I have written these steps with a name. So first step is polarization, because the positive and negative charges, they are separated. This is not charged yet because total number net is still 0, only separation of charge, right? So it hasn't touched, and we're not going to touch with that. Rather, what we're going to do is now we're going to provide a path for electrons to either flow into the object or out of the object. Okay, So two things can happen. Either electrons from the ground can come to the object or go to the object. So it doesn't have to be connected with wire. You can just touch it. So your body, our body also has a lot of charge, okay? So that charge can transfer to the object, or some electrons can transfer from object to our body. That can happen, okay? So now you just provide that path by connecting with wire, or you just touch with some conductor, okay? Just finger is good. Now what happens? So in this case, you see the electrons from the ground is coming to this and neutralizing some of this positive charge. So once it comes, what happens? It's going to combine with this positive charge. One electron combines with one positive, makes it neutral. Both of them are there, but now that extra charge is gone. Another comes, neutralizes that. Another comes, neutralizes that. Now less and less positive charge. So when we connect, this positive charge is not moving here. We're not showing that. If you say that, then that's going to be wrong, because positive charge cannot move through the solid object, right? So keep that in mind. So now what happens? Instantly, it does not take a lot of time. Within a nanoseconds, what happens? All these are going to be neutralized, okay? However, let's say if you were to bring a negatively charged rod, how that's going to be different? How would that be different? Think about it. If your rod has, let's say, negative charge instead of this positive charge, here what would be the case? Then this negative electron gonna repel these electrons there and leave the positive charge there. So this would be positive charge, positively polarized on this side and negatively polarized on that side. Okay. And then when you connect wire, what's going to happen? Now these electrons are dying to get away from here. So they're just going to go out. So they're going to flow to the ground. Okay. But let's just keep talking about the positively charged rod. Okay. So now all is gone. What you do next? If you remove this rod, at this situation, what's going to happen? Let's say you brought it closer and removed it back. What's going to happen? The extra electron that came, now see, oh, there are a lot of electrons. We do not want to stay there, right? So they get repelled and they're going to go back. So this is not going to be charged. However, if you want to make it charged, then you need to prevent these electrons from neutralizing those. So for that, what do? You disconnect the grounding. Or if you tossed, remove your finger. Okay. So now what's going to happen? In this case, there is now more negative charge inside the sphere. And since this rod did not toss, these electrons cannot go. They are just outside the fence. Okay. Some people are crazy about celebrities, right? So if you find your celebrity, you cannot just meet, right? You may have to stand in the line outside the wall, some sort of fence, right? So that's what these electrons are doing. They are attracted. They want to meet so bad, but they cannot, because there is no path for them to go there. So they are stuck there. And now, since we removed this, what happens? They cannot flow back to the earth as well. So now we are left with this extra negative charge on that sphere or conductor, and we say, okay, it is charged now. Remember all this picture. In my note, I haven't drawn these bases because drawing bases is not that easy. So I have just drawn these spheres and the rod in my note, okay? But assume that these are there. Or else what's going to happen? If you touch directly to them, then the electrons are going to go to your body or come from your body and going to neutralize any extra charge. So this kind of thing not going to happen. So you have to be holding with some sort of insulator, and this thing has to be a steel conductor or metal. Okay. So when we brought positive charge close to this thing and went through these 4 steps, what happened? This got negatively charged. Remember, in the case of conduction, what happens? If you touch with positively charged, this becomes positively charged. If you touch with negatively charged rod, this becomes negatively charged. But in case of induction, we did not touch. What happened? It became oppositely charged. And since there has to be flow of electron, you cannot charge electrons using this induction method. You can make them polarize a little bit, but no charging. Okay. Anything you like to add or ask on this one, folks? Is it clear what's going on? Take a moment, look, and understand what's going on. See if you can explain what goes in there. So if you don't have question, I do have question. Okay. So here is question for you. Oh. Okay, 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. So we have a big distribution, but mostly we have C as a majority. So let's see what's going on here. Let's suppose, like many of you, I'm also thinking C is correct answer. Am I right or wrong, and why? Can somebody help me? Why C is right or wrong?
I don't know if my thinking is correct on this, but I would say that it would be not charged at all. They would just be polarized because it wasn't touched to the sphere and it was just brought near.
Right. So let's say if we think about it, so they are touching each other. So that means they are conductors and touching each other like they are like one object, right? So when you bring positive charge, there are going to be extra negative charge here and extra positive charge there, right? So that's the first step. That's what's going to happen, right? And then charge rod is then removed, it says. So now it's not touched, but removed. Once it is removed, what happens? See, they were separated because there was this positive charge. It attracted this negative charge, leaving positive charges behind. But once they are gone, what happens? See, these negative charges, they repel each other. Since nothing is attracting, celebrity is gone, then crowd disperse, right? So they're going to go back and neutralize that, okay? So it's just polarized, yes, just like you said, okay? So that means both of them seems to have zero charge. If you separate before move the, you move the rod before you separate. See, this what step you do is important here. See here, the rod was removed before the sphere was separated. However, if we had gone like this as a step B and this as a step C, then this would have been positively charged and this would have been negatively charged. So in that case, they would be charged. But in this case, what happened? We did not separate. Because of that, what happens? We don't have charge. Ooh. They are moving, we cannot see. So sometimes it's hard to make sense, right? But yes, the reader, that was good explanation. Okay, so let's see. So E is correct answer in this case. So C would have been correct if we had separated the sphere first. So that's why it is very important we pay attention to how things are happening, what's going on, okay? Okay, so I have another question here. Take a time and write it down if needed. Write down numbers, scribble numbers. You have 2 minutes for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Are you excited to see? I am. Okay. Again, C has a more choice than the other. I don't know the answer because I didn't do my homework. I didn't write down the numbers, okay? So let's write it down. So it says spheres P and Q are tossed together. So these are both conductors because they are made up of metals. Metals are conductors. So when they mix, what happens? There is negative 2 nanocoulomb, there is positive 4 nanocoulomb. So that means net. So they gets added. One is positive, another one is negative. So added means they get subtracted. So net in this case, the total gonna be positive 2 nanocoulomb. When they are tossed together, that's what we have. Now the next step, so when tossed, now separated. So they are basically conductors, right? And they are kind of identical spheres. So we can say if we were to separate, now what's going to happen? They're going to distribute their charge equally. So that means when they separated, P going to have positive 1 nanocoulomb and Q going to have positive 1 nanocoulomb. Now what happens? So this is P, this is Q. And then now what's happening is Q and R are tossed together. So now this Q goes there and touches with R. It has a positive 1 and this one has a negative 1. So touching means now they are adding together, mixing together, right? So that means positive 1 and negative, so net becomes 0. Okay, so now the question is afterward, the charge on sphere R, this one is 0. Excuse me. Because of that, this one is also 0, right? So both of them have 0 charge because net is 0. There is no extra charge anymore to distribute. However, P still has that 1 nanocoulomb. So the question is about R. It has 0 means this time, yes, looks like C is correct answer. We do not want to miss a step. We do not want to go in different order. It has to be in the order it's said in the question. Okay. Okay, anything you like to add or ask on this one? All right, then I have another question for you. You can do this with the comb as well. Comb your hair. It has to be dry hair, not oily or wet. And bring comb closer. And this has to be thin, thinnest possible. Oops. This one has to be thinnest possible. Let's do 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see. How did we do? Mostly see. So water molecules are a little bit polarized, but not charged always. Okay. Net charge on polarized object is still 0. So yes, C is correct answer. It gets more polarized once you bring this positive charge, this balloon, that's charged balloon, doesn't matter whether it's a positively charged or negatively charged. What happens? It's gonna pull that. So charged object always pulls an uncharged object at the beginning, just like we saw on that demo video, okay? So uncharged object comes here in contact, and then once it comes in contact, the charge transfer takes place, and they have same charge now because this is because of the conduction, and then they repel, right? So anyway, did I choose the answer here? Looks like I did. So I have here another question before I show you this demo on this PHET Fate website. It's really cool website. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see, what did we get here? So A, B, and E. So 1A has a net charge, well, B is uncharged. So net charge, let's say, when can an insulator have net charge? We can charge by friction, and insulator can have net charge, right? And conductor, we can charge it, so it can have net charge. So both insulator and conductor can have net charge, okay? Just by saying net charge, we cannot tell whether it's a conductor or an insulator. How about when it is uncharged? So neutrally, everything is neutral unless we charge them, right? And so that means both insulator and conductor can be uncharged, okay? So that's why, based on that, we cannot just tell which one is which, okay? So that's why in this case, the farthest one, E, is correct answer. Okay. Anything you like to add or ask? So there is a question. So can anything ever be uncharged? Yes. Uncharged means no net charge. Okay. Uncharged means no net charge. So keep that in mind. We say object is charged only when there is one kind of charge more. So that means charge imbalance. Charged means charge imbalance. Just being charged does not mean it's a charged. There has to be net charge for an object to be charged. Okay. So just like we said, if we have one positive, negative, so they have charge. That does not mean they are charged. For this to be charged, you have to have either one extra or more, like positive charge, or you have to have extra negative charge for this to be charged. Okay. I hope that answer your question. Yes. Net charge 0 is uncharged. You got that right. So now I'm at this FIT website. And by the way, looks like based on the email, probably that email came before class, I forgot. So assignments, where do you find? There. See here, there is pre-class section, there is playground section. So these are the practice one. Okay, these are the practice ones underneath playground. So they are named like P1, P2. Pre-class, they are named PC1, PC2, right? And they are going to be weekly. They are named as a W1, W2, and so on. So there are 3 different types. All of them going to be in this window here. Okay, so back to this one here. So what happens is you can open this. Right now, this balloon here, you see, the balloon has equal number of positive and negative charges. This means it's uncharged, net charge 0. Okay. Bring this balloon close to this. What happens near the wall? Not many charge. So because of that, we don't see much movement of that charge over there. Okay. Both of these are insulators. So we don't see much happening here. But let's say if I bring that to woolen sweater, for a sweater, then what happens? Balloon pulls out the electrons. Now, if you bring to the wall, what happens? It pushes the negative charge away because negative charge repels the negative charge, and positive charge just remains there, so that way this balloon can stick on the wall. So you can do several cool such experiment in this website, okay? So just search for PHET Colorado and look for subject. So you have, this kind of thing for chemistry and physics. I'm not sure about biology, okay? So you can find this. So folks, so it's already 50. So I'll let you go. I'll see you next class. So make sure to do the the survey I have sent you, and that can be found right here at the home and this pre-semester survey. Okay, so that way I can start showing you the notebook LM and how to use it, and I'll ask you to use it right here in the class. Okay, And make sure you bring a laptop to the class rather than just sitting on the phone, okay? Okay, folks, I'll see you next class.